Okay, now I think it's working. Okay, so this is 569. And this is a little bit different than the previous ones we had because we do have an extra force this time. In the previous problems, we just had one force. We do have an initial velocity of 0, so that means our arbitrary constants are probably going to go to 0. And we have a tension in the string. It's a function of time, so it's force. And so t equals 0, there's no force. And then we start to increase it linearly with time. Our weight is constant. So what's going to happen at first is if there's no tension in this, and this is the only force acting on it besides the tension, it's going to start to fall. And then as this increases, we're going to reach a point where this is equal to the weight. At that point, the acceleration is 0, but the velocity may not be 0. So I've taken the mass of 3 kilograms and multiplied by 9.8 meters per second squared. I get 29.4 newtons, so that's my weight, and that's always the same. So we sum the forces in the y direction instead of just equaling a force. In this case, we have the tension pulling up, and I didn't show it, but we have, the y direction is positive. And so this is positive and this is negative. Okay, so we're going to solve for the acceleration just like we had done previously. So we divide both sides by the mass. So we get that this tension is a function of time minus this w. Okay. So just like before, we're going to, well, in this case, we're going to plug the numbers in. So T is 36 newtons per second times tension is 36 newtons per second times T. The weight is constant divided by the mass. So this is going to be 12, and this is going to be something less than 12. Actually, what we get is 9.8. So acceleration is initially is going to be negative 9.8 meters per second squared, and then it's going to become less negative, and then it's going to become positive. And this actually is to show the units, just to convince myself that these have the correct units, because this is going to be time as seconds, and we need to end up meters per second squared. So we've got newtons per kilogram seconds. That's this one. If we put in for newtons, we put a kilogram meter per second squared. We take the reciprocal of this, which is that, and you multiply that, you get meters per second cubed times seconds, and you get meters per second squared. But what I'm actually doing is I am going to rewrite these units in something. So instead of 12 newtons per kilogram seconds, it's going to be 12 meters per second cubed. And likewise, newtons per kilogram are the same as meters per second squared. So I'm going to put meters per second squared in there. So my acceleration in the y direction is now 12 meters per second cubed times t minus 9.8 meters per second squared. Okay, here we go again. The acceleration is the derivative of the velocity in the y direction with respect to time. So multiply both sides by dt, end up with this differential equation. Integrate both sides. This is just going to be the velocity in the y direction. We'll plug in our expression for the y acceleration right here. And so we get 12 meters per second cubed t minus 9.8 meters per second squared, whole thing times dt. These are constants, so I can take those out. The integral of t is going to be t squared over 2, and the integral of 9.8 meters per second squared, that's a constant, so I can take that out. And then I will have the integral of just 1 dt is t. So integrate it. This becomes t squared over 2. This becomes just t. I have my arbitrary constant. Now, V0 is 0, so that's going to make C equal 0. So this is my general solution. This is my particular solution, given the initial conditions I have. And then they asked for what is the velocity after 1 second. So all you do is stick 1 second in. Do the calculations. And I guess I haven't finished this one yet. Okay. Well, let me get the book out. And I'll do it now. So I just need to find my calculator in my book. So this, what problem is this? 569. Okay, so let's see what they're asking. What is the velocity of the box at t equals 3 seconds? Okay, that was pretty easy. What is the velocity at t equals 3 seconds? Well, all we have to do for that is we just have to plug in 3 seconds into the equation. So v sub y at 3 seconds is 6.0 meters per second cubed times 3 seconds squared minus 9.8 meters per second squared times 3 seconds. And what do we get? So, actually I never did calculate the previous question. Okay, so I've actually got to calculate this first. So I get 6 times 1 minus 9.8. That's easy. I guess 6 minus 9.8. So after 1 second, we're still falling. We're falling. Okay, so it's negative 3.80 meters per second. So at t equals 0, you can see the velocity is 0, but then it starts to fall, so it's negative. And I think the reason they're asking for what happens after 3 seconds is you'll see that it goes back the other direction. So you get 6 times 3 squared, which is 9, minus 9.8 times 3, and I end up at 24.6. So v sub y at 3 seconds is positive, so that's going back up. Whereas initially it was going down after 1 second. Okay, let's see what the next thing they're asking here is. What is the maximum distance the box descends below its initial position? At what value of t does the box return to its initial position? Okay, well you can see the reason they asked us to do this first time is to show you that somewhere between 1 second and 3 seconds that the velocity goes to 0. And so what we're going to do is we're going to set this equal to 0 and figure out what the value of t is. So that the velocity is 0, that means that's when it starts to turn around and go the other direction. Okay, so you get 6 meters per second cubed t squared minus 9.8 meters per second squared times t. So we can factor out t on the right-hand side, and you'll get t times 6.0 meters per second cubed times t minus 9.8 meters per second squared. So you can see at t equals 0, it's 0, which we already know. That's the initial condition. So the other case is when this goes to 0, and what I'm going to do is I'm going to just move this to the other side, so you get 9.8 meters per second squared, so the negative becomes positive. I set this equal to 0, and you can see that t is going to be 9.8 meters per second squared divided by 6.0 meters per second cubed, and you get whatever that ratio is, 9.8 divided by 6, and you get 1.63 seconds. So then we saw that over here. 1 second it was going down, at 3 seconds it was going up. At 1.63 seconds it is stopped. Okay, so was that what they asked us, or did they ask us what is the maximum distance? Okay, so to calculate distance, we're actually going to have to integrate this thing. So we know that dx dt, which is the velocity, is equal to 6.0 meters per second cubed t squared minus 9.8 meters per second squared t. Multiply both sides by dt. And then you integrate both sides, so we'll get x. And then we're going to integrate this. I'm just going to write them in here instead of copying them down. If you want to copy them down, you can. Okay, so we integrate that. So you'll end up with the constant, first constant. Integrate t squared, you get t cubed over 3. Then we have 9.8 meters per second squared times t squared over 2 plus c, but this is 0 because x is 0, and actually I probably should be using y. So let's do that. dy dt. Since this thing's a vertical thing, so we'll say y. So y is that, but at t equals 0, y equals 0, so that goes to 0. So our particular solution is this. We can go ahead and divide 6 by 3. That's 2.0 meters per second cubed times t cubed minus 9.8 divided by 2 is 4.9. And meters per second squared times t squared. Okay, so now we take our time, 1.63 seconds. So y of 1.63 seconds, we get 2.0 meters per second cubed times t, 1.63 seconds cubed minus 4.9 meters per second squared times that. Let's see, we get 2 times 1.63 cubed minus 4.9 times 1.63 squared. And this should be negative because otherwise it's not going down. So we do get a negative number. So the maximum distance that it goes down is negative 4.36 meters. Okay. So that is hopefully part B. And it says, what value of t does the box return to its initial position? So what we do there is we want to set this equal to 0. So the initial position was 0, so now we figure out, we'll actually use this equation here. So you get 2.0 meters per second cubed times t cubed minus 4.9 meters per second squared times t squared. We'll find the values of t where they go to 0. Well, you can see I can factor out t squared, and I'll end up with 2.0 meters per second cubed times t minus 4.9 meters per second squared. So t equals 0 is one solution, and that's my initial condition. Yeah. And then the other one is where this goes to 0. So again, like we did before, to save one step, I'm just going to move this, set this equal to 0, move that to the other side. You get 4.9 meters per second squared. Solve for t by dividing 4.9 meters per second squared divided by 2.0 meters per second cubed. And we can get actually 2.45 seconds. And again, that makes sense because we went to the minimum distance, the furthest distance y after 1.63 seconds. So it should be greater than that by the time we come back up through there. And you could calculate the velocity too. If you got that time, you could then use that time in the velocity equation to see what the velocity was as you passed through that point. And anyway, gotta make sure I find the answer in the back of the book. So I forgot what the number of this problem was. Let's see, a 569. And I think the first question was, what was the first question? I think what the velocity was after 1 second and 3 seconds. Okay, so that was the first question. 563. Nope. 559. Still got the wrong problem. Oh, here we go. 569. Negative 3.8 meters per second. Cha-ching. The second one was 24.6 meters per second. Cha-ching. Time for it to go to the lowest point, 4.36 seconds. Oh, 4.36 meters. So yeah, it was 1.63 seconds, and I had to do this, and I got to 4.36 meters. Yep. And the final one is how much time did it take to get back to its original position? 2.45 seconds. Hey, I should teach this class. Okay, so that's it.